We are finishing up chapter 3, covering the universal law of gravity. Oh, this topic comes after discussing Newton's 3 laws of motion, which describe the relationship between forces and motion, and introduce the concept of inertia. Those 3 laws of motion do not explain where gravity comes from. Gravity is considered a fundamental force, and its explanation is separate from other fundamental laws, like laws of motion or Kepler's laws. The the fundamental relationship that we will talk about will be based on the following criteria: that the universal law of gravity is always an attractive force. It is gravity never repulses two objects. There's no such thing as anti-gravity or gravity being able to, like I said, repulse or push two things away. Uh, this is noticeably in contrast to the electrostatic force and the well-known concept of opposites attracting and like repelling, which happens with charged particles, electrons and protons. Gravity simply doesn't work that way. In that regard, gravity is a simpler force because it's only attractive. It also means that gravity can and will continue to grow as more mass accumulates. A really fascinating and wide-ranging concept that we will occasionally return back to as one of these overarching themes, and namely that gravity has this ability to gradually grow stronger and stronger and stronger until it pushes up against the very limits of the physical laws that we have derived and observed. So in this case, we have to illustrate this concept and to talk about more details of the universal law of gravity. Let's imagine two masses, which aptly can be imagined as floating in space, because if we have them floating in space, we don't have to worry about any other gravity forces. They can just be out on their own. Teresa, did you have a question?
Yes, I have a question. I only see three Newton laws of only three Newton laws. Is this one
Mhm.
will this one be considered the fourth, his fourth law?
Not not formally, no. But sometimes, but not regularly, it's
Okay.
referred that way. But more as like a joke than as a serious.
Yeah, that's because I was
Yeah,
reading in the book and I only see three that are written
correct.
in our book. And I was like, would this be considered his fourth law? Okay.
Yeah, it's and more than it just like the name and what whether people call it that or not. Um, it's important, I think, and good to think of it as separate. You got Newton's 3 laws, and then you have this law called the universal law of gravity, or Newton's universal law of gravity. Yep. So back to our two rocks in space. That's what we want to think of them as. So they will experience an attractive force towards each other because gravity attracts. No matter how big they are, no matter how far apart they will always be attracted to each other. Often that attractive force is so small, it would be insignificant, too small to measure. An example of that is the fact that when we're on Earth, everything around us is gravitationally attracted to us. Even, two people experience a incredibly small gravitational force pulling them horizontally towards each other. They're standing on flat ground, right? You don't notice that force because the force of attraction towards the Earth, a much larger mass, is dominating. And that's the direction and the force that you experience and know as just gravity. It's, when you're on the surface of the planet, gravity always points down. It technically doesn't. Everything around you, every bit of mass, mountains, for example, will have their own gravity. It's just so much smaller because they are so much smaller. Okay. So both objects are attracted to each other. They feel the same size force pulling them together. So good kind of reference, especially since it's been, since last week, since we saw Newton's laws. Which of Newton's three laws, first, second, or third, or you could give me their names, but which of them is this last sentence referring to? The fact that the two rocks feel the same size force pulling them together. Which of Newton's laws makes this so it has to be true? I can chat here. Okay. All right. So we had a vote for the second and for the law of inertia. Well, I love the guesses, but those are actually the two that it's not, which means we've narrowed it down. Teresa, did you have a opinion?
Yes, I believe is the universal law of gravity.
Well, that's not the one of the three, though.
Oh, sorry, number three.
Okay, yes, it is number three. Yeah, I mean, well, as I said, it's not the law of inertia, which is one. That was Maxwell's yes, and then Denise said it was two, which is that F equals ma. It's neither of those, therefore it has to be the third one.
Which is the action of reaction, right?
Yes, yes, yep, exactly. And if you think about it, maybe some of you can see why it would be action reaction, and that's just because we've got this, action we could think of as the arrow on the left, right? Maybe the green arrow acting on the first rock, and then the reaction to that force would be the green arrow acting on the other rock. So if that doesn't seem like a typical action reaction pair, it's just because there's no contact. But that's the way gravity works. Gravity does not require contact. It just exists through space. And so you do not need to touch something in order to feel its influence of gravity. That's actually one of the key ideas about gravity, is that it's essentially sends out a signal that you respond to, that your mass responds to. Very, cutting edge modern physics involves the detection and measurement of gravitational waves, which are an experimental confirmation of this idea that gravity, really exists in the same way that light does, in that it can just spread out through space, right? So that's the idea, is we have always gravity action acting with action, right? But acting with these force pairs, action reaction pairs. Those action reaction pairs cause movement. So, and why is that, right? Well, because these are both the same force. They have to be the same force. If both rocks in this case have the same mass, then they'll both experience the same acceleration. I don't want to spend an inordinate amount of time on this, but I do want to point out that, okay, if we give these both a value of m measured in kilograms, then and as I mentioned before, they're both going to experience the same force, just different directions, as stated by Newton's third law, or in confirmation with Newton's third law. And if they are the same mass, then they'll both experience the same acceleration. So then I would have the acceleration of the rock on the left would be a, and then that would just equal F divided by m. And this, of course, is using Newton's second law. So we see that, the universal law of gravitation is often combined conceptually or quantitatively with other of Newton's laws of motion. Okay, or I should say, with any of Newton's laws of motion, because gravity is not a law of motion on its own. You got to combine it with them to get motion. And then the acceleration of this one would just be identical because its mass is identical. If they had different masses, if, for example, the rock on the right was more massive, then we'd have something like this, where we could imagine this one having a different value. All right, good. And we'll make it a just uppercase M to represent that it has a larger mass, so big M, and then you would divide by that value in order to get your acceleration. So this is an important point, at least as far as this small portion of the class. Obviously, would be a really important point in the physics class, but less so here. Regardless, what the point is that although two objects will experience the same force because of gravity, and that's always going to happen anytime you're going to interact with something gravitationally, anytime the moon interacts with the earth gravitationally, and anytime the earth interacts with the sun, anytime a person standing on the surface of a planet interacts with that planet, every time the forces are equal, but the accelerations are not necessarily equal, because with all the examples I just gave, moon, earth, sun, person, planet, well, the masses are definitely not equal. Therefore, the accelerations aren't. In each case, the smaller mass will experience the bigger, sometimes much bigger acceleration, and the larger mass will experience a small, sometimes insignificantly small acceleration. So if m is really big compared to little m, big M compared to little m, then we're going to have a huge disparity in the accelerations. The example that I always give of this is that if you're just right now, standing on the surface of the earth, if maybe you're sitting, but if you stand up and you jump when you're airborne, the only force other than a tiny bit of air resistance that's acting on you is gravity pulling you down. Kind of like, imagine like this block being pulled in, or rock, being pulled in the down direction, which would be, to like the left in this case. Well, as that rock gets pulled in that direction, or you think of yourself getting pulled towards the earth, well, there has to be a equal and opposite force acting on the earth itself, which means that the earth is getting pulled towards you. And it really is. You are exerting the same force on the earth as the earth is exerting on you. You are two separate bodies and you're interacting together. It's just that the Earth is a trillion times more massive than you. So the acceleration that it experiences from a single person jumping on its surface is nothing. It would move less than an atom's distance. And so there's no actual movement. And also, that whatever small amount of, movement there is on the surface of the Earth would always, essentially cancel itself out. So there you go. Now, the actual equation. Okay, so far we talked about the concept. Now let's quickly look at the formula. So the universal law of gravity has the following formula definition. What does it tell us? Okay, well, we have a constant as the first letter. I mean, obviously the first letters, if we read from left to right, is just the force, all right? But the whole equation just defines the force. So the equation is about giving us the value of the force, so defining it. And then it's equal to this constant, g, always shown as uppercase g, to distinguish it from lowercase g, which is a gravitational acceleration. Right? But uppercase g is universal, whereas lowercase g for Earth is 9.81 meters per second squared. That's called, just surface gravity on Earth. Well, that only applies to Earth. This this value here applies to the entire cosmos. It has applied to everything since the Big Bang. It fundamentally, sets the way our universe works, along with a few other similar constants. which are sometimes called like the tuning constants of the universe. The numerator, after we multiply by g, is the product, right? So the actual, multiplication of the two masses that are interacting. So in the case of the two rocks, it would just be their masses multiplied together. This big G out in front need not be out in front. Since it is just multiplication, we could put it up in the numerator and it could be just G M1 M2. But this way is almost the only way you'll see the formula written, just for clarification and to call attention to the significance of the leading constant. All right. And whereas the M's here are considered variables because they vary, right? Where of course G does not. It's always the same. And so if we wanted the Earth and the Sun, then our M1 would be the Earth, for example, M2 would be the Sun. The order doesn't matter because it's multiplication. Finally, in the denominator, we have the distance between the two objects. Okay, that's what r is. So in this case here, r would be the distance between the two masses at any instant. Because obviously, once the two masses start moving, r is going to change. And so we'd have to recalculate the force at the gravitational force at different separation distances. But if we just consider this particular snapshot in time, we've got our two masses separated by a distance r. And part of the reason we use the letter r is because it often is a radius when the gravitational force leads to some orbit, which is commonly the case in astronomical phenomenon, that we have r being the radius. But it's not always, but we still use r. R would be measured in meters. All right. So here we have the sun and the earth, M1 and M2. Distance r separating them. Okay. And just to highlight the importance, that r is squared. So notice that it's not just r, it's the square of r. And that means that as the distance changes, the force will change quickly or dramatically because of the changes in r. What I'm getting at is that it's that squared relationship causes a strong mathematical dependence. If you think of it, it's like a parabolic dependence because you're squaring it. The name of this relationship is an inverse square proportionality, which I'll mention again in a couple slides. But let's check your understanding. Which pair of asteroids feel a larger gravitational force? The pair on the left, where the two asteroids have a mass m and are separated by distance r, or the pair on the right, where they have masses m and 2m and are separated by a distance of 2r. So which pair?
Do we put it in the chat?
Yeah, I was opening up the chat right now, so you can put it there, or you can say it out loud. Either way.
I'd say number one because I could have sworn I heard you say that when it's closer, it's stronger. When it's farther apart, it's like weaker. But maybe I don't know if I'm right.
Yeah, and that would be like a cut and dried answer if the masses weren't different, right? But here you in
Oh,
but yeah, just don't miss that. Although you're still right. So let's see. So we've got, and then people are saying the number one for the left pair have the stronger. Yeah. Oh yeah. Well, I mean, the people aren't saying number one. They're saying number two, which is the pair on the right, which is correct. So everyone in the chat has gotten it correct so far. Yep. So I'll tell you now. If you're it's number two is the correct answer right there. All right. And the reason is, let's see, hold on. Larger gravitational force. No, wait, what? No. But did I read it wrong? Let's reread it. I probably just got my wires crossed there. So which pair, because this didn't happen last time I did it. All right, let's cover these slides. So which pair of asteroids feels a larger gravitational force? And it's the oh yeah, it's the pair on the left. Yeah. Oh wow. Maybe I just because everybody had that answer.
I,
Why did you all hear it? I mean, clear that up.
Understood it wrong, teacher. I meant to say the one on the left, which is closer. I don't know why I said number two.
Okay, no worries. I know. And then it threw me off too, so I can relate. So yeah, so just to make sure that that makes sense to everybody, when you look at it, and we can actually really quickly show it quite well, is that over here, so the stronger force, the one on the left, the one where the distance between them is r, because over here our force is just going to be, and so we'll make it a kind of like a proportionality. All right, not worry about G, remember that little symbol. And so here, we got the two M's, right? So it's just we have just M and squared because we're multiplying the two of them together, and then R squared. So that's how strong the force is for the pair on the left. The pair on the right, the force between them is quite different, or at least, it's going to show up pretty differently because we're going to have M times 2M. So that'll be 2M squared. All right. But then the distance, the 2 itself gets squared because it's the distance squared. Here, the m squared is just because, the two objects are either the same mass or a multiple of the same mass. But here it's 2r, and you can put in parentheses to show it, why this happens. But you're squaring the 2r, so that means that if we were to rewrite it, we end up having, still the 2m squared up top, but we have 4r squared in the denominator. So if we were then to, go ahead and cancel out the 2 with the fact that 4 is 2 times 2, we'd end up with a 2 remaining in the denominator, showing us that the force for the pair on the right is half as strong. The gravitational force for those two objects is half as strong as for the two objects on the right. Sorry, as on the left. Well, right, left. So there you go. And what is this stress? What does it highlight? The importance of distance, right? So doubling the distance has a bigger effect than doubling the mass.
So it
At least,
doesn't
yeah.
matter if the distance is bigger, it doesn't matter how big the mass is. It's always going to be
No,
stronger.
no, not no. It matters. It just doesn't matter as much.
Okay.
Because I mean, think if I made this like 8m, then it would be big enough that the extra mass would compensate for the extra distance. You see?
Oh, okay.
Yeah. It's just that if the change in the distance is the same as the change in one of the masses, then the change in the distance is more important because that's what happened here. We went from R to 2R, and we went from M to 2M. So we doubled one of the masses and we doubled the distance. And we saw that doubling the distance had a bigger effect.
So would you have to solve for both basically to see what that difference is and which one is still
Yes, yes. You have,
okay.
yeah. And with practice, often you can do it in your head. But if that isn't the case, then you would have to like do what I did and plug the numbers in for each case. Okay, so that's the idea, and I think we have another one that will be similar enough that we'll see in a second. But before we consider other combinations of distance and mass, let's take a look at this example here. We have a astronaut that's halfway between two masses, and we're being asked a question. So we're being asked if or what direction does the gravitational pull on our astronaut, what direction does she feel the pull? And your options are 1, which is the yellow arrow, so getting pulled to the left, 2, the green arrow, getting pulled to the right, neither direction, or you give up. All right. We got one vote in chat so far. get a few other answers. All right. Cool. All right. So yeah, a little bit of variety, some getting pulled to the right, the left, but mostly people say neither direction. So let's see. Neither direction is correct. Can anyone explain why? Does anyone want to justify their answer, maybe, that said number three?
Is it because of the third law where there's an equal and opposite reaction from Newton's law?
No, no. It's not because of the third law. There's no the forces shown, like the yellow and the green, are not a force pair. Just to quickly say why without going down a whole nother direction is because to have an action reaction pair of forces, it has to be between two masses. So, like I exert a force on something, that object exerts a force back onto me. Well, the two forces shown on the astronaut are both exerted on one object and come from two other objects. So there's three things here. There's three objects, and then just two of the forces are showing. So we know it's not an action reaction pair.
So if one mass was bigger, like say the right side mass was bigger, would that change the astronaut staying in the middle?
It would if the mass on the bigger if the mass on the right was bigger, then that would be the direction that the astronaut would move. Would be towards the bigger mass. Absolutely would. Yep. And then we saw Maxwell says in chat, Newton's second law is the reason. Yep, that's exactly it. Yeah. And Teresa, what did you want to say?
Is it because the astronaut is weightless?
Well, the only reason that they are weightless is because of Newton's second law.
Right. Okay.
So yeah, so it's like a cause and effect. You can't say that number three is the answer because they're weightless. Rather, number three is the answer because the forces cancel out. And if the forces cancel out, then Newton's second law says that the acceleration must be zero.
Because acceleration of a body is proportional. Oh, okay.
Is proportional to the force and the mass. And in this case, it's the net force is zero. The
Okay.
net force is zero. There is a balancing of forces, canceling of forces. These are potentially pretty subtle ideas. I know from teaching them physics. So if they're bogging you down too much, then you have to move on because you can spend weeks on these ideas. So just get them as much as you can and remember that they are only really 10-15% of the course at most. Especially kind of real subtle aspects of this. On the other hand, if you do get it, that's great. That's an asset. So it all comes
Excuse,
down to
excuse me.
please.
Sorry, I know this is off topic, but is there a quiz today?
Yep. Coming up in a few minutes, and then
Oh,
we're
okay.
yeah, of course it's taking longer, but we'll be doing it soon.
All right. Thank
So
you. So good.
all right, so let's go. Yeah, and there's a few more examples, but I think this is where I cut it off with the other class as well. So we'll do it. We'll just do this last slide, and then I'll say, hey, there's other examples, but you can look at them on your own time. So if you remember the proportionality symbol, which I just mentioned myself a minute ago, we saw it when we were looking at basic physical laws like even velocity. Well, it can be used again to kind of dive into the universal law of gravitation and really highlight how we can think about the relationship of or the dependence on mass and the dependence on distance. What I mean by that is the following. Okay, this is just the distance speed times time I was referring to. Let's skip over this right now. Yada, 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 yada. Okay. Okay. But then for our universal gravitation, here it is, the universal gravitation formula. Here it's an equation. Part of the reason it's an equation is because of that big G, that universal gravitation constant, an experimentally determined value, and a really small number. If you saw that scientific notation, I meant to refer to it, but it's a really small number. It's 6.67 times 10 to the negative 11. So, there would be, if you move the decimal place after the six, you're going to have 10 zeros behind the one before you even get to it. So it's considered a tiny value, which is part of the reason why gravity is so small for small objects. And you need planet-sized masses to get noticeable gravity. But back to proportionalities, if you just were to only focus on one mass, then you'll see that there is a direct proportionality between the force of gravity and mass. The bigger the mass of object one, which is, either object, so it could be, the moon in the case of the Earth and the moon, or a person in the case of a person and the planet, you have a direct relationship. We sometimes call this a direct proportionality or a linear proportionality. It's linear like a line. Same thing for the other mass, because the two masses are always interchangeable. They're not unique in the equation. You just need to clearly define which is which. But in both cases, if you increase the mass, the gravity increases. So if you double m1, you double the force of gravity. If you double m2, you double the force of gravity. All right. And that also means, by the way, I'll talk about the last one in just a second, but if you were to double both masses, so if I doubled, and this goes back to the question that we had a few minutes ago. I think it was Kylie had it, about when does mass matter, or does it never matter as much as distance? Well, if you doubled both m1 and m2, well, then you'd be quadrupling the force, right? Because double m1, twice the force of gravity, double m2, twice the force of gravity. So, double both of them, 4 times the force of gravity. And then the last thing to highlight here is this inverse because it's in the denominator, squared relationship between the gravitational force and the distance. So if you double the distance between two objects, the gravitational force they experience is 1/4 as strong. If you triple the distance, the gravitational force they experience is 1/9 as strong. You quadruple the distance, the gravitational force they experience is 1/16 as strong. Because in each case, you're squaring it and it's in the denominator. All right. And that's what they're talking about here. And then they do the same proportionality for Kepler's laws. So then the last thing I want to talk about is tying together Kepler's law, third law in particular, with the universal law of gravitation. So remember, Kepler's third law was a proportionality between the period squared of an orbit and the semi-major axis. And that's a good thing. So in the quiz that we're going to take, remember semi-major axis, remember your definitions of ellipses. The first correction or improvement on Kepler's third law is to consider the importance of mass, because that way you can consider other systems besides just comparing to Earth, or comparing Earth to the other planets that orbit the same star, our sun. Okay? But the real complete version, and the one that's in the homework that's due tomorrow, is called Newton's version of Kepler's third law. And what Newton's version does is it takes universal gravitation, which we can see kind of in the fact that the universal gravitational constant is included, the importance of mass is considered, and this 4 pi squared just comes out of the mathematical derivation. It comes from basically the calculus that's used to derive this formula. But what we have here is a formula that looks a lot like Kepler's third law, because it's still got the a cubed and the p squared. The only difference is that it now has this coefficient around right in front of the p squared. So multiplied by the period squared, because here p is still period, a is still semi-major axis, but this value right here is the only addition. And what this version of Kepler's third law can do is it can relate the semi-major axis and the period between any two, or between, or for rather, any orbiting object. So you can talk about the moon orbiting around any planet. You can talk about planets orbiting around other stars. So it's a totally, applicable formula for any orbiting system. The M here is just the mass of the bigger object, because this formula is still an approximation, as most formulas are. You can always have some improvement on them. And so here we're ignoring the mass of the object that's orbiting. So if it was the moon, we'd ignore the mass of the moon, and M would just be the mass of the Earth. And that's a very reasonable approximation, and it will get you answers that are not going to be significantly different than if you did try to include the mass of the moon, for example. So you only include the bigger mass, the thing that is being orbited, instead of the thing that is orbiting. Okay, so any questions on this formula? Well, while you're thinking about that, I'll tell you my plan here is I know we're kind of approaching where we normally do the break, but I propose we just take the quiz first, then just segue right into a break, and so when we can come back, we can then just do chapter 4 for the rest of the class. So we'll have our 15 minutes, and then that'll take us up to 9:15, 5-minute break, 9:20, and start on chapter 4. Hopefully that sounds good to you all.
Sounds good.
Okay, additional gravitation problems. You can do those if you're interested. Let's stop this recording.